Picture yourself standing at the base of a massive stone wall, so perfectly fitted together that even after thousands of years, you cannot slide the edge of a credit card between the seams. No mortar, no metal fasteners, just stone upon stone, holding strong against earthquakes, storms, and the relentless passage of time. How is it possible that ancient civilizations without blueprints, without machinery, without any of the technology we take for granted created structures that continue to baffle and inspire us today? This is the enduring mystery of ancient engineering, a testament to what human ingenuity can achieve when paired with patience, observation, and an intimate understanding of the natural world. From the soaring pyramids of Egypt to the intricate terraces of Machu Picchu, these builders worked with little more than stone tools, raw strength, and a profound connection to their materials. They didn't see the absence of modern adhesives or fasteners as a limitation. Instead, they turned it into an advantage, developing methods that relied on precision, balance, and a deep knowledge of geometry and physics. Their creations were not just buildings, they were expressions of cultural identity, spiritual belief, and technological brilliance, monuments meant to last for eternity, and many of them have done just that. In this video, we're going to journey across continents and centuries to uncover the secrets of these master builders. We'll explore how they cut and moved multi-ton stones with astonishing accuracy, how they designed structures to dance with earthquakes instead of collapsing, and why they chose methods that have proven more durable than much of what we build today. This is a story about resilience, innovation, and the sheer will to create something lasting. It's a reminder that true advancement isn't always about having the most advanced tools, but about understanding the fundamental principles of our world. So settle in and get ready to see history's most breathtaking constructions in a whole new light. But what exactly do we mean when we talk about ancient engineering marvels? It's a term we often use, but it represents something incredibly specific and profound. This was the art of constructing massive, lasting structures using nothing more than the raw materials provided by the earth and the strength of human hands. Think about that for a moment. No steel beams, no concrete mixers, no power tools, just stone, wood, rope, and an almost supernatural level of patience and skill. The core principle was precision. Instead of gluing blocks together with mortar or binding them with metal, these builders focused on cutting and shaping each piece so perfectly that it would lock into its neighbor, creating stability through perfect fit and friction. It was a world where geometry was the ultimate tool, and a keen understanding of balance and weight distribution was more valuable than any modern adhesive. This approach wasn't a primitive stepping stone to something better. It was a deliberate and highly sophisticated choice. From the breathtaking pyramids of Giza to the imposing, earthquake-defying walls of the Inca, these structures are a testament to a deep, intuitive knowledge of physics and material science. The builders knew the properties of their stone intimately, how it could be split, how it would wear over centuries, how it would react to seismic shifts. This mastery allowed them to create monuments that weren't just built to last, but were designed to become a permanent part of the landscape. The absence of mortar wasn't a shortcoming. It was the very secret to their longevity. Modern materials can crack, crumble, and degrade, but a perfectly balanced dry stone wall can shift and settle without collapsing, dancing with the earth rather than fighting against it. This ancient philosophy offers us powerful lessons in resilience and innovation today. It shows us that true sustainability isn't about creating more advanced synthetic materials, but about working in harmony with the natural world, using local resources with incredible intelligence and respect. These creations are more than just piles of rock. They are a language of stone, speaking across millennia about what humanity can achieve with observation, collaboration, and an unwavering dedication to craft. To truly grasp the brilliance of these ancient builders, we must step into their world and understand not just how they built, but why. These colossal structures were far more than mere buildings. They were profound expressions of a civilization's soul, etched in stone for eternity. In an age without modern nation-states or digital networks, a society's identity, power, and very connection to the cosmos were physically manifested in these monumental projects. For the pharaohs of Egypt, a pyramid was not a simple tomb. It was a divine machine, a ramp to the heavens designed to launch a god-king's soul into the afterlife among the imperishable stars. Its perfect geometric shape, its alignment with celestial bodies, and its staggering scale were all deliberate choices to communicate eternal power and order in a universe that could otherwise seem chaotic. Similarly, the great ziggurats of Mesopotamia functioned as artificial mountains, bridging the gap between the earthly realm and the gods above. Every mud brick laid was an act of devotion, a communal effort to please the deities who controlled the floods and the harvests. This spiritual imperative demanded perfection. You couldn't use a temporary, inferior material like mortar for a structure meant to touch the divine. It had to be as eternal and unchanging as the gods themselves, which is why the precision of fitted stone became a theological necessity as much as an engineering one. This deep spiritual significance was woven into the very fabric of daily life and social order. In the Andes, the Inca Empire's architectural prowess was a direct reflection of its political and cosmic worldview. The seamless stonework of sites like Machu Picchu or the fortress of Sacsayhuaman was a powerful statement of control over nature, over subject populations, and over the very geological forces of the earth. The ability to make massive stones fit together without a gap demonstrated a supernatural level of skill that reinforced the ruler's divine right to govern. The construction process itself was a ritual. The quarrying, transport, and placement of stones were often accompanied by ceremonies, and the structures were frequently aligned with solstices or other astronomical events, turning entire cities into intricate calendars. In this context, the choice to forego mortar was a deliberate one. A mortared wall is rigid, it cracks under stress and reveals its weakness, but an Inca wall, with its complex interlocking joints, could shift and settle during an earthquake, then settle back into place, a dynamic, living entity that danced with the tectonic forces of their mountain home. This wasn't just smart engineering. It was a symbolic demonstration of resilience and harmony with Pachamama, or Mother Earth. Across the ocean, we see the same principles at play in the megalithic temples of Mortar or the soaring Parthenon in Greece. These were not passive sculptures but active centers of community, worship, and knowledge. Stonehenge, with its ring of massive sarsen stones, likely served as a celestial observatory, a burial ground, and a place of pilgrimage, its construction spanning generations and requiring a coordinated effort that must have defined the cultural identity of the people who built it. The Greek Parthenon, though it used metal clamps, primarily relied on the incredible precision of its marble blocks and the genius of its optical refinements to create a sense of perfect harmony and beauty, a temple to Athena that celebrated human reason and order. In each case, the method of construction, the patience, the skill, the communal effort was inseparable from the meaning of the structure itself. The knowledge of how to cut, move, and fit these stones was sacred knowledge, passed down through apprenticeships from master to apprentice, often guarded as a valuable secret. This wasn't a hobby, it was a vocation, a calling that tied an individual's life to a project that would outlast them by millennia. When we look at these sites today, we are not just looking at clever puzzles of rock. We are reading the deepest hopes, fears, and beliefs of an entire culture, written in a language of stone that has refused to be silenced by time. The immense investment of labor and resources only makes sense when we see these structures as the very heart of a civilization's existence, the physical anchor for their worldview, and their most audacious attempt to reach for the eternal. Nowhere is this philosophy of sacred engineering more breathtakingly realized than in the stonework of the Inca Empire. High in the Andes Mountains, they achieved a level of precision that seems to defy logic, creating walls where massive, irregular blocks fit together so perfectly that the seams are virtually invisible. To stand before the fortress of Sacsayhuaman or the terraces of Ollantaytambo is to witness a stone puzzle crafted on a monumental scale, a testament to a culture that viewed the very act of building as a form of reverence for the earth. The Incas worked primarily with two of the hardest materials imaginable, granite and limestone. Their toolkit was astonishingly simple bronze chisels that were softer than the stone they cut, stone hammers, and abrasives like sand and water for polishing. This makes their achievement all the more incredible. They didn't overpower their materials with superior technology. They understood them through patient observation and a process of meticulous trial and error. Artisans would slowly shape each block, likely by repeatedly tracing the outline of a neighboring stone onto it, and then painstakingly grinding away minuscule amounts until the fit was flawless. This technique, known as ashlar masonry, resulted in joints so tight that not even a razor blade can be inserted between them. But this wasn't just an artistic pursuit, it was a stroke of seismic genius. The Andes are one of the most earthquake-prone regions on the planet. A rigid, mortared wall would crack and crumble under the immense stress of tectonic shifts. An Inca wall, however, is designed to breathe. During a quake, the individually shaped stones in a perfectly fitted wall can shift and sway minutely, dancing with the tremors, and then settle back into their original positions once the shaking stops. The entire structure flexes without breaking, a dynamic and resilient system that has kept these walls standing for over 500 years. The mystery only deepens when we consider how these stones were moved and placed. At sites like Ollantaytambo, we see enormous red granite blocks, some weighing well over 50 tons, quarried from a mountainside across a deep valley and a roaring river. The logistics are staggering. The prevailing theory is that they used an army of laborers, dragging the stones on wooden rollers or sledges along earthen ramps. Some researchers suggest they might have leveraged the landscape itself, creating intricate systems of ropes and counterweights to inch these behemoths into place. The most famous stones at Sacsayhuaman are so large that the Spanish conquistadors, upon seeing them, refused to believe they were placed by human hands and attributed the work to demons or giants. The true methods remain one of history's great puzzles, a testament to the Incas' extraordinary organizational skills and their ability to mobilize and coordinate vast workforces through a shared cultural and spiritual purpose. Beyond the how, we must also consider the why of such immense effort. Each perfectly fitted stone was more than a building block, it was a statement. In the Inca worldview, the ruler was a divine being, and his power was demonstrated through impossible acts of engineering that tamed the raw, powerful landscape. A wall that could defy earthquakes was the ultimate symbol of this power, showing a harmony with the forces of nature that mere mortals could not achieve. The resulting structures are not only incredibly strong but also possess a profound, quiet beauty. The way the stones interlock with their multifaceted faces and subtle curves creates a mesmerizing play of light and shadow across the surface. It is architecture that is both brutally powerful and delicately sophisticated, a permanent record of a civilization that mastered its world not through force, but through an intimate and patient conversation with stone. While the Incas were mastering the art of fitting irregular stones in the Andes, an entirely different but equally awe-inspiring engineering philosophy was being perfected on the sands of Egypt. The Great Pyramid of Giza is arguably the most iconic ancient structure on Earth, a monument so vast and precise that it held the record as the tallest man-made building for over 3,800 years. Built for the pharaoh Khufu around 2560 BCE, it represents the absolute pinnacle of a building tradition that had been refined over centuries. What is truly staggering is the sheer volume of material involved. The pyramid is composed of an estimated 2.3 million individual blocks of limestone and granite, each one weighing an average of 2.5 tons. That is equivalent to the weight of 2,500 pickup trucks, and yet some of the stones used in the king's chamber are colossal granite monoliths hauled from a quarry over 500 miles away, each weighing up to 80 tons. The logistical challenge of this project, even by today's standards, is almost incomprehensible. So how did they move these titanic blocks without the wheel, without iron, and without powerful machinery? The Egyptians were masters of simple physics, leveraging their understanding of leverage, friction, and inclined planes. Their primary tools were copper chisels and saws, copper being a relatively soft metal, along with stone dolerite hammers for pounding and grinding the hard limestone. To move a single 80-ton granite block, they would have employed a massive sledge, a team of hundreds of laborers, and a carefully prepared pathway. There is compelling evidence that these pathways were made slick by pouring water onto the sand in front of the sledge, dramatically reducing friction and making it possible for a large team to pull the immense weight. To lift these blocks into place as the pyramid grew taller, they almost certainly constructed massive ramps made of mud brick and limestone chippings. Archaeologists debate the exact form of these ramps, whether they were straight, zigzagging, or wrapped around the structure's sides, but these temporary engineering works were just as impressive as the permanent monument they helped create. The coordination required was a monumental feat of administration, directing a skilled workforce of thousands, not slaves as was once popularly believed, who were housed, fed, and organized with military-like precision. But the true genius of the pyramid builders lies not just in moving the stones, but in placing them with breathtaking accuracy. Before a single block was laid, the site had to be perfectly leveled. The Egyptians achieved this with astonishing simplicity by cutting a grid of shallow channels into the bedrock, filling them with water, and then carefully chiseling the entire site down to a uniform water level, creating a foundation that is flat to within less than an inch across its entire 13-acre base. Then came the alignment. The Great Pyramid is oriented to the cardinal directions with a margin of error of just 1/15 of a single degree. This is not a lucky guess. It is a demonstration of sophisticated astronomical knowledge. They likely used a tool called a merkit, a forked sighting stick, to track the movements of specific stars, bisecting their arc across the sky to find true north. This celestial connection was everything. The pyramid was not merely a tomb. It was a resurrection machine, a physical ramp designed to project the pharaoh's soul directly into the heavens to join the eternal, unchanging circumpolar stars, known as the imperishable ones. Every aspect of its design served this spiritual purpose. This spiritual drive for perfection is most evident inside the pyramid itself. Deep within the heart of the massive stone pile lies the king's chamber, built entirely from immense blocks of red granite. The precision here is otherworldly. The joints between the granite blocks are, in many places, only 1/1000th of an inch wide, finer than a human hair. The surfaces are flawlessly flat, and the corners are perfect right angles. The chamber's roof is made of 9 gigantic granite slabs weighing a combined 400 tons, engineered to distribute the immense weight of the masonry above and prevent the chamber from collapsing. Leading to this sacred space are a series of narrow, sharply angled shafts known as the air shafts, though their purpose was almost certainly ceremonial, not practical, possibly aligned with specific stars important to the pharaoh's journey to the afterlife. This incredible internal precision, hidden from view, proves that their commitment to perfection was not for external glory but for a divine function. They were building for eternity, crafting a stone vessel meant to withstand not just the elements but time itself to ensure their king's immortality. The fact that it still stands, a testament to their success, over 4,500 years later, is the most powerful tribute to their engineering philosophy ever conceived. While the Egyptians and Incas were mastering the art of monolithic precision, a different kind of architectural revolution was taking shape around the Mediterranean, one that would use geometry and gravity to create vast, open spaces that defined public life for millennia. The Greeks and Romans took the principles of dry stone construction and elevated them to an unprecedented scale and sophistication, building not just tombs and temples, but entire cities, aqueducts, and amphitheaters that formed the backbone of their empires. Their secret wasn't just in cutting stones to fit, but in understanding the fundamental physics of how weight could be channeled, distributed, and ultimately conquered through intelligent design. The Greeks were the master theorists, the philosophers of stone. Their most iconic contribution, the post and lintel system seen in temples like the Parthenon, is a breathtaking exercise in precision dry stone work. Each massive marble column was built from individually carved drums, stacked without any mortar and held together only by a central wooden peg. The weight of the entire structure above was transferred perfectly down through the center of each column. But their true genius lay in their subtle understanding of human perception and structural dynamics. They employed optical refinements that are almost imperceptible but crucial. Columns that bulge slightly in the middle to counter the optical illusion of looking pinched, and a platform that curves upward at the center to appear perfectly level. Every surface was angled, every line was curved, all to create a structure that felt harmonious and stable to the human eye. This wasn't just art, it was neuroscience and physics expressed in stone, a building designed to feel eternally solid because its builders understood how we see. The Romans looked at Greek elegance and saw potential for raw power and imperial ambition. They were the practical engineers, the builders of an empire, and they took the dry stone concept and reinvented it with their two most iconic innovations, the arch and concrete. While they did use a primitive form of concrete, their most enduring structures still relied on the core principle of fitted stone. The arch is the ultimate expression of dry stone genius. It is a structure that should, in theory, collapse under its own weight, but by carefully carving wedge-shaped stones called voussoirs, the Romans created a system where each stone's weight pushes against its neighbor, transferring the tremendous load down through the curve of the arch and into the supporting piers on either side. The entire structure is held in a perfect state of compression, a balanced clash of forces where gravity itself becomes the binding agent. This single invention allowed them to span distances the Greeks could never dream of, building the vast, cavernous spaces of the Colosseum, where 80,000 people could be seated, and the soaring aqueducts like the Pont du Gard in France, which carried water for 30 miles across deep river valleys. These weren't just buildings, they were gravity-defying marvels. None of this would have been possible without a toolkit that was remarkably advanced for its time. The Greeks developed the dioptra, an intricate surveying instrument that was the ancestor of the modern theodolite. It allowed them to measure angles and level terrain with astonishing accuracy, ensuring their temples were perfectly aligned and their foundations true. The Romans perfected the treadwheel crane, a massive human-powered machine that could lift weights of several tons using a complex system of pulleys and gears, operated by men walking inside a giant hamster wheel. This machinery allowed them to hoist the massive stone blocks for their amphitheaters and temples into place with an efficiency that still commands respect. But perhaps the most overlooked testament to Roman dry stone prowess is lying beneath the ground of their entire empire, the roads. The famed Roman roads were masterpieces of layered, mortarless construction. They started with a deep trench, then laid a foundation of large stones, followed by layers of progressively smaller gravel, sand, and flint, all compacted into a solid, durable mass. The top surface was often paved with polygonal basalt stones, fitted together so tightly that they formed a smooth, seamless surface that could withstand the pounding of armies, merchants, and time itself. These roads were the internet of the ancient world, enabling the rapid movement of troops, the flow of trade, and the spread of culture across continents. They were built to last, and many are still visible today, a network of stone veins that once pulsed with the lifeblood of an empire. The legacy of Greek and Roman dry stone technique is all around us, in the arched bridges of medieval Europe, the domed cathedrals of the Renaissance, and even in the fundamental principles of civil engineering still taught today. They proved that durability and beauty are not opposing forces, but two sides of the same, perfectly cut stone. Far to the north of the Inca Empire, in the dense jungles and high plateaus of Mesoamerica, another wave of architectural genius was reaching its zenith. The Maya and the Aztecs, separated by centuries and geography, shared a similar profound vision: to build monuments that pierced the heavens, connecting the world of humans with the realm of the gods. Their approach to construction was a breathtaking fusion of brute force, delicate artistry, and celestial mathematics, all achieved with the simplest of stone tools and an organizational prowess that still leaves historians in awe. Unlike the Incas, who worked with hard igneous rock, the Maya primarily had access to limestone, a relatively soft material that could be quarried with stone axes and shaped with chert or obsidian chisels. This might sound easier, but it presented its own unique challenges. Limestone is brittle and can fracture unpredictably, yet the Maya artisans mastered it, carving massive blocks and fitting them together in towering pyramidal temples that rose like mountains from the flat jungle canopy. At the heart of their building technique was the corbel arch, a clever and elegant solution to creating doorways and interior spaces without a true keystone arch. They would lay each successive course of stone slightly inward from the one below, gradually leaning the walls toward each other until they could be capped by a single stone at the top. This created a distinctive V-shaped arch that efficiently channeled the immense weight of the structure down and outward into the supporting walls. It was a design that limited the size of interior spaces compared to the Roman arch, but it was incredibly stable and perfectly suited to their architectural vision, creating those iconic narrow, towering doorways that seemed to draw you into another world. The scale of their ambition is best witnessed at a place like Chichen Itza, where the Great Step Pyramid known as El Castillo dominates the landscape. This is not just a pile of rocks, it is a precision astronomical instrument made of stone. Each of its 4 sides has 91 steps, which, combined with the shared platform at the top, equals 365, the number of days in a solar year. Furthermore, during the spring and autumn equinoxes, the interplay of sunlight and shadow on the northern staircase creates the illusion of a massive serpent slithering down from the heavens to earth, a direct representation of the feathered serpent god Kukulkan. This is the ultimate expression of Maya engineering, a structure that is geometrically perfect, spiritually profound, and astronomically accurate, all built without mortar, metal tools, or the wheel. The stones were cut so precisely that they hold the entire massive form together through friction and perfect balance. The logistical feat of its construction is staggering. Quarries were often miles away through difficult terrain. Large workforces would have used levers, rope, and rolling logs to transport these multi-ton blocks. Earthen ramps built and rebuilt as the pyramid grew taller were the likely cranes of their day, allowing teams to haul stones into their final positions. This was a society capable of mobilizing and feeding thousands of workers, all dedicated to a project that served a cosmic purpose, ensuring the continued order of the universe through their alignment with the celestial cycles. Centuries later and further north, in the Valley of Mexico, the Aztecs were applying this same Mesoamerican engineering philosophy, but with a distinct imperial flair. Their capital, Tenochtitlan, was a marvel of urban planning built on an island in the middle of a lake, requiring even more innovative foundations. For their towering Templo Mayor, they drove wooden pilings into the soft lake bed to create a stable base, and then began stacking stone upon stone. While they did occasionally use a lime-based cement, their primary construction method for load-bearing walls was still precise dry stone masonry. They would often build a core of rubble and earth, then face it with expertly cut and fitted volcanic stone blocks, frequently adorning them with dramatic sculptures of their deities. The Aztecs were master stone carvers, and their buildings were literally covered in narrative art, from coiled serpents to skull racks, making the architecture itself a text that communicated their power and mythology. The transport of materials here was an even greater challenge. The massive stones for the Templo Mayor were quarried from the mainland and brought across the lake on enormous barges, an operation that required a navy of boats and countless laborers. The coordination was a testament to the Aztec state's immense organizational power, its ability to command resources and labor from across its empire. For both the Maya and the Aztecs, the act of building was inextricably linked to their cosmology. A pyramid was not just a temple, it was a sacred mountain, a recreation of the primordial landscape from their creation myths. The precision of the stonework, the alignment with the stars, and the immense effort invested were all acts of devotion, meant to maintain the delicate balance of the cosmos and please the gods who controlled the sun, the rain, and the very cycle of life and death. Their structures were the physical anchors of their universe, and they built them to last for eternity, a promise that, in many cases, they have spectacularly kept. Across the vast and diverse continent of Asia, ancient builders developed their own unique dialects in this universal language of stone, adapting dry construction techniques to some of the world's most challenging climates and most deeply held spiritual beliefs. In China, the ambition was imperial in scale, a drive to physically manifest the power and permanence of a dynasty. While later sections of the Great Wall were reinforced with mortar, its earliest and most resilient stretches were masterclasses in dry stone engineering. Builders employed a technique known as rammed earth or hangtu for the wall's core. This involved pouring a mixture of earth, gravel, and clay into wooden frames, which was then pounded into an incredibly dense, concrete-like hardness by teams of laborers wielding heavy tamping rods. This core was then faced with locally quarried stone blocks, carefully selected for their size and shape, and fitted together without any adhesive. The genius of this method was its flexibility and durability. In the freezing winters and scorching summers of northern China, materials expand and contract. A rigid, mortared wall would crack and crumble under this thermal stress, but a dry stone wall could shift minutely, absorbing the movement without structural failure. The irregular laying pattern also allowed for excellent drainage, preventing water from seeping into the core and freezing, which would otherwise spell its doom. This wasn't just a wall, It was a living, breathing part of the landscape, designed to endure the relentless forces of nature and human conflict for centuries. Meanwhile, on the Indian subcontinent, a different kind of stone poetry was being composed. Here, the drive was not for military defense, but for divine celebration. The temples of Kojorajo, built by the Chandela dynasty around 1,000 years ago, are perhaps the most stunning examples. From a distance, they appear as intricate, organic sculptures that grew from the earth rather than being built upon it. This illusion is the result of an almost superhuman commitment to interlocking stone construction. Artisans worked primarily with sandstone, a relatively soft stone that allowed for detailed carving but required immense precision to bear weight. Each block was meticulously dressed, with protruding tenons carved on one side and matching mortises hollowed out on the other. When assembled, these blocks locked together like a three-dimensional stone puzzle, creating a monolithic structure that relied on compression and intricate joinery rather than binding agents. This was absolutely essential for surviving the region's powerful monsoon seasons and seismic activity. The temples are covered in a breathtaking tapestry of carvings, gods, goddesses, celestial nymphs, and mythical beasts, all carved in situ after the stones were set. This reveals another layer of their genius. The structural and the artistic were completely inseparable. The carvings aren't merely applied decoration. They are integral to the stone itself, meaning the entire edifice had to be designed and engineered to perfection before a single artist could make a mark. The process of building these Asian marvels was a spectacle of human coordination and ingenuity. For the Great Wall, workers established quarries directly along the construction route, using fire-setting techniques to crack large granite and limestone slabs from cliff faces. They would light fires against the rock and then douse them with water, causing the stone to fracture along predictable lines. Transporting these stones across mountainous terrain involved systems of ramps, sledges, and levers, with human chains passing materials hand over hand up the steepest slopes. In India, the construction of a major temple was a community-wide endeavor that could span generations. Massive wooden scaffolding shrouded the rising structure, and teams of oxen dragged stone blocks from quarries miles away. A key innovation was the use of the Persian wheel, a geared water-lifting device that was adapted into a simple but effective crane system, using a rope wound around a large wheel turned by animals or humans to hoist heavy stones into position. The master architects, known as Stapathis in India, worked from detailed mental plans and sacred geometric diagrams called mandalas, ensuring that every proportion of the temple was cosmically significant and structurally sound. Their knowledge was a closely guarded secret passed down through families, blending mathematics, astronomy, and spirituality into a single, sacred science of building. The legacy of these Asian techniques did not stay within their borders. The principles of Chinese rammed earth construction traveled along the Silk Road, influencing fortifications and architecture across Central Asia. Similarly, the design and structural principles of Indian temple architecture spread with Hinduism and Buddhism into Southeast Asia, inspiring the construction of awe-inspiring complexes like Angkor Wat in Cambodia, which itself is a masterpiece of layered, fitted sandstone blocks. This cross-pollination of ideas created a rich tapestry of innovation, proving that the desire to build magnificently and permanently without synthetic binders was a universal human impulse, one that connected cultures across vast distances through a shared language of stone, gravity, and breathtaking ambition. But how did these master builders translate their grand visions into reality, ensuring that a pyramid would rise to the heavens without toppling or an arch would span a ravine without collapsing? The answer lies not in complex machinery, but in a profound and intuitive command of geometry and mathematics, principles they treated as a sacred language spoken by the universe itself. For these ancient engineers, math was far more than abstract calculation. It was the physical manifestation of cosmic order, a set of rules that governed everything from the growth of a nautilus shell to the path of the stars, and by embedding these rules into their structures, they were literally building harmony into the very fabric of their world. They didn't have computers to run finite element analysis or laser levels to ensure perfect plumb. Instead, they wielded tools of beautiful simplicity. A knotted rope, for instance, became a precision surveying instrument. By tying knots at specific, standardized intervals, they could quickly measure out right angles on a colossal scale using the principles of the 3-4-5 Pythagorean triangle. Stretching the rope to create a triangle with sides of 3, 4, and 5 units guaranteed a perfect right angle at the corner, allowing them to lay out the vast, perfectly square foundations of a temple or the cardinal alignment of a pyramid with nothing more than fiber and faith. As simple a frame level, a weighted plumb bob hanging from the peak of a wooden frame could tell them if a surface was truly horizontal, while water-filled trenches provided an infallible leveling reference across acres of uneven ground, their still surfaces mirroring the perfect flatness of the horizon. This geometric wisdom was applied with breathtaking sophistication. The architects of the Parthenon didn't just build a rectangular temple, they engineered an optical illusion of perfection. Knowing that perfectly straight lines would actually appear to sag to the human eye, they incorporated subtle curves into every element. The platform bows upward slightly in the center, the columns swell gently in the middle and tilt inward, and every line is a calculated curve. This meant that there wasn't a single straight line or right angle in the entire structure as we would measure it with modern instruments, yet to anyone looking upon it, the building appeared flawlessly straight, solid, and harmonious. This was neuroscience and advanced geometry expressed in marble, a building designed to feel eternally true. Similarly, the proportions of these structures were often dictated by ratios believed to be divinely beautiful, like the golden mean, approximately 1:618 to 1. This ratio, found in the spiral of galaxies and the arrangement of petals, was consciously incorporated into the floor plans and facades of Egyptian and Greek temples, creating a subconscious sense of balance and beauty that we still respond to today. It was a way of ensuring that a building wasn't just structurally sound, but also spiritually resonant, a true reflection of the natural order. This mathematical foundation was the absolute key to their most daring structural innovations, particularly the arch and the dome. To build a vast, unsupported roof of stone or a bridge that could span a river without any glue holding it together required a terrifying leap of faith, a faith grounded in precise calculation. The Roman arch is a masterpiece of applied geometry. Each wedge-shaped stone, called a voussoir, had to be cut to an exact, identical angle so that the collective force of their weight would be transferred perfectly around the curve of the arch and down into the sturdy piers on either side. A single stone cut even a degree off could disrupt this delicate balance of compressive forces and cause the entire structure to buckle. The same genius applies to the magnificent domes, like the one atop the Pantheon in Rome. This vast unsupported concrete sphere, still the world's largest unreinforced concrete dome, was engineered as a series of diminishing concentric rings, each one a perfect circle that supported the one above it, channeling the immense gravitational loads downward and outward in a continuous flow of force. In India, this geometric mastery took a different form in the breathtaking stepwells like Chand Bayori. These are inverted pyramids carved down into the earth, featuring intricate, symmetrical staircases of thousands of perfectly identical steps descending on three sides to a water source below. The stability of these subterranean marvels, which could easily collapse inward from the pressure of the surrounding earth, relied entirely on the precise angles of the steps and walls, each one acting as a buttress for its neighbor in a complex, repetitive geometric pattern. This was not guesswork. It was the result of centuries of accumulated empirical knowledge, a deep library of understood principles passed down from master to apprentice through hands-on practice and oral tradition. They learned by doing, by observing what worked and what failed, and they encoded these lessons into the very proportions of their designs. Their intuitive grasp of physics, of load, thrust, compression, and tension, allowed them to create seemingly impossible forms that have stood for millennia, a silent testament to the power of a mind that understands the deep, mathematical music of the world. The very first and most critical decision an ancient engineer made wasn't about design or placement, but about the stone itself. This was a profound conversation with the landscape, a choice that would determine not just the aesthetics of a structure, but its very soul and its chance of surviving the millennia. They weren't just picking rocks, they were selecting partners in a project that would outlast empires. They understood the unique personality of each material intimately. For the eternal, unmoving heart of a pyramid or a divine statue, they sought out granite incredibly hard, resistant to weathering, and capable of taking a high polish, but brutally difficult to work. For the vast majority of a structure where detailed carving was needed, they turned to limestone or sandstone, softer, more workable, and able to be shaped with relative speed. And for intricate decorative elements or delicate statuary, they might choose alabaster or marble, prized for its beautiful veining and ability to be rendered into flowing, lifelike forms. This wasn't a random selection. It was a meticulous balancing act between the desired permanence, the available labor, the intended artistic expression, and the sheer logistical nightmare of transport. A local, softer stone might be chosen for a city wall simply because it was there, saving thousands of hours of effort, while a pharaoh would demand granite from a quarry 500 miles away for his burial chamber, accepting the immense cost for the promise of eternity. Once the perfect stone was identified, the next challenge was to convince the earth to let it go. Quarrying a multi-ton block from living bedrock with primitive tools is an act of both violence and delicate precision. One of the most widespread and clever techniques was fire setting. Workers would build a roaring fire directly against the rock face, heating the stone until it was scorching hot. Then they would suddenly douse it with water or vinegar, causing the rock to contract rapidly and fracture along predictable lines. The thermal shock would create cracks and fissures, allowing them to isolate large, manageable blocks from the mother rock. It was a method that required careful control. Too much heat could shatter the stone into useless fragments, while too little would have no effect at all. After the initial cracking, the real artistry began. Using stone dolerite hammers, balls of a rock harder than granite itself, teams of workers would pound along the intended fracture line, effectively pulverizing the granite into dust along a narrow channel, hour after hour, day after day, until the block was finally freed. For softer stones like limestone, they used copper chisels and saws, though the copper was soft and would have required constant resharpening and replacement. To accelerate the cutting, they employed a simple but effective abrasive, sand. By pouring wet quartz sand into the cut and sawing or drilling with a copper blade, they transformed the soft metal tool into a mere holder for countless microscopic, ultra-hard cutting particles. The sand did the real work, grinding through the stone with patient, relentless efficiency. This combination of thermal shock, percussive force, and abrasive grinding allowed them to extract blocks of astonishing size and regularity from the earth, the first step in a journey that would end in a monument for the ages. But freeing the block was only half the battle. Now it had to be moved, and this is where the logistics become almost unbelievable. Imagine a 100-ton granite obelisk newly separated from the quarry bed. How do you move it without a crane? The answer lies in a beautiful application of simple physics and raw, coordinated human power. The most common method involved wooden sledges, massive, rugged platforms that could be dragged. But dragging 100 tons of stone across sand or soil creates impossible levels of friction. The ancient Egyptians likely discovered a brilliantly simple trick. They poured water onto the sand in front of the sledge. The water saturates the grains, making them lock together and creating a firm, slick surface that dramatically reduces the friction. Wall paintings show exactly this scene, a colossal statue on a sledge being pulled by a large team of laborers, with a person standing at the front pouring liquid onto the path. For moving these sledges, they used teams of oxen and gangs of men pulling on heavy ropes, inching the monument forward. To distribute the weight even further and ease the movement over uneven ground, they likely placed the sledge on a track of wooden rollers, tree trunks laid side by side. As the sledge moved forward, rollers from the back would be carried to the front, creating a continuous, moving pathway. For truly treacherous terrain or steep slopes, they may have constructed massive earthen ramps, turning a vertical challenge into a manageable, gradual incline. When the journey involved water, the challenge changed. The Egyptians transported their famous Aswan granite obelisks down the Nile on enormous, purpose-built barges. These vessels were feats of engineering in themselves, capable of bearing a load of hundreds of tons. They would have been towed by teams of smaller boats with dozens of rowers, fighting the current to deliver their precious cargo to the construction site. The final act, lifting these blocks into position, is one of history's great mysteries. For the pyramids, the prevailing theory involves the construction of massive, linear or zig-zagging ramps made of mudbrick and limestone chippings. As the pyramid grew taller, the ramp was extended upward and outward, providing a sloping road for teams to drag the stones to their final resting place. For placing the massive lintels at Stonehenge or the crossbeams of a Greek temple, they probably used a combination of levers, earthen mounds, and a technique called parbuckling, where ropes are looped around a stone and teams pull from either side to slowly tip it upright. Every step of this process, from the quarry to the pinnacle of a pyramid, was a breathtaking symphony of coordination, patience, and applied physics. It was a process measured not in days or months, but in generations, a testament to a society's unwavering commitment to a vision so grand that its fulfillment was worth the labor of 1,000 lifetimes. Yet for all their ingenious problem-solving, the true masterstroke of these ancient builders was not in any single tool, but in their profound understanding of how to use them in concert. They possessed a holistic knowledge system where the right tool was matched perfectly to the material and the task. A stone hammer might be used for the initial rough shaping of a granite block, but the final, hair's breadth precision would be achieved with a combination of copper chisels for detailed work and a slurry of sand and water for the patient, final polishing. This wasn't a haphazard process. It was a carefully choreographed sequence of force and finesse. The evolution of these toolkits wasn't driven by a desire for novelty, but by the relentless demands of their projects. As structures grew taller and stones grew larger, the simple lever had to be refined. The basic inclined plane evolved into complex systems of ramps and causeways. The need for perfect alignment in ever more ambitious temples led to the invention of sophisticated measuring devices. This was a continuous cycle of innovation. each new construction challenge pushed the boundaries of their existing tools, which in turn spurred the development of new techniques, which then enabled even more audacious architectural feats. Their workshop was a living laboratory, and their legacy is a powerful reminder that technological advancement is not always about inventing something entirely new, but often about perfecting the simple, elegant application of fundamental principles to solve a problem with breathtaking efficiency. Yet the true marvel lies not in the sheer number of hands, but in the intricate social machinery that directed them. These were not chaotic mobs of forced labor as often depicted in popular fiction, but highly organized, stratified societies operating with a precision that would impress a modern project manager. At the top of this pyramid of effort were the master architects and skilled artisans, the intellectual engineers who transformed spiritual vision into geometric reality. These individuals possessed a lifetime of accumulated knowledge, the secrets of astronomy for alignment, the mathematics of load distribution, the properties of local stone. They were the undisputed authorities on the site, directing the work with an almost priestly status. Beneath them were the specialized craftsmen, the quarrymen who could read the grain of a granite cliff to extract a perfect block, the stone cutters who could shape it with astonishing accuracy using only simple tools, the transporters who mastered the physics of leverage and friction, and the final fitting teams who possessed the patient, meticulous skill to lock multi-ton stones together like perfect puzzle. This division of labor was not arbitrary. It was a system refined over generations, ensuring that every individual was deployed according to their utmost capability, maximizing efficiency on a scale we can scarcely imagine today. The systems that mobilized these vast workforces were as sophisticated as the engineering itself. In ancient Egypt, the state operated a system known as corvée labor, a form of tax paid not in grain or gold, but in time and muscle. For part of each year, particularly during the annual inundation of the Nile when farming was impossible, farmers would be conscripted to work on state projects. This was not solely an act of coercion, it was a deeply embedded social contract. In return for their labor, the state provided food, shelter, and a sense of participation in a divine mission that benefited the entire kingdom. The promise of a well-fed existence during the off-season and the spiritual merit gained from building a god-king's eternal home were powerful motivators. Similarly, the Inca Empire perfected the mita system, a rotational labor tax that drew upon millions of subjects across its vast Andean territory. Communities were required to send a quota of workers for set periods to contribute to public works projects, building roads, terraces, or majestic temples. This system was the backbone of the empire, efficiently distributing the burden of massive construction across its population while simultaneously integrating diverse, conquered peoples into a unified imperial identity. By working side by side on a project that glorified the Inca state and its divine ruler, laborers from different regions forged a common purpose, strengthening the social fabric of the empire itself. Beyond these state-mandated systems, there was also a powerful element of voluntary communal effort, a phenomenon seen in structures like the megalithic temples of Mortar or the great mounds of North America. In these cases, construction likely served as a seasonal gathering point, a sacred festival of work that reinforced community bonds and collective identity. The act of building together became a ritual in itself, a physical prayer that strengthened social cohesion and fulfilled a shared religious duty. The psychological impact of participating in such a grand endeavor cannot be overstated. For an individual laborer hauling a stone for the Great Pyramid, the back-breaking work was transformed from a mere task into a personal contribution to a project of eternal, cosmic significance. They were not just building a tomb, they were ensuring the pharaoh's successful journey to the afterlife, which in turn guaranteed the continued stability and prosperity of Egypt itself. This shared belief system turned a construction site into a pilgrimage destination, a place where every participant, from the master architect to the lowliest laborer pouring water on the sand, could feel connected to something far greater than themselves. The economic benefits were also profound. These projects stimulated local economies, creating demand for food, tools, pottery, and textiles to support the workforce. They functioned as massive public works programs, providing sustenance and purpose, and likely fostering innovation as artisans and workers from different regions exchanged techniques and ideas. The social dimension reveals that these ancient wonders were not just triumphs of engineering, but triumphs of human organization and collective spirit. They stand as permanent monuments to our deepest human impulses, to create together, to believe together, and to build a legacy that will long outlast our own individual lives. This deep, intuitive connection to the environment is perhaps the most profound lesson ancient engineers left for us. They didn't build against their surroundings, they built with them, viewing the landscape not as an obstacle to be conquered, but as a partner in a grand, collaborative project. This philosophy of integration began with the most fundamental choice, material selection. By sourcing stone, timber, and earth almost exclusively from the immediate vicinity, they achieved a level of sustainability we are only now rediscovering. Think about the massive granite blocks of an Inca fortress, quarried from the very mountain it was built upon, or the limestone pyramids of Egypt, rising from the Giza plateau whose bedrock provided their core material. This drastically reduced the energy expenditure and environmental cost of transportation, but more importantly, it guaranteed that the building materials were already in perfect harmony with the local climate. A stone that has spent millennia weathering the specific conditions of a region, its freeze-thaw cycles, its prevailing winds, its humidity, is already pre-adapted for longevity. Using it in construction wasn't just convenient, it was a masterstroke of biomimicry, using the landscape's own evolved resilience to create structures that would endure. This adaptive genius is brilliantly illustrated in two very different yet equally effective systems, Inca terracing and Roman aqueducts. High in the Andes, the Incas faced incredibly steep, erosion-prone slopes. Their solution wasn't to flatten the mountains, but to sculpt them into a series of elegant, stair-like terraces. These were far more than just farmland. They were a complex geo-engineering project. Each terrace wall, built in that signature interlocking dry stone style, acted as a massive retaining structure that prevented the thin, precious topsoil from washing away down the mountainside during heavy rains. The stones themselves absorbed heat during the day and released it slowly at night, creating microclimates that could protect crops from frost. They also provided perfect drainage, ensuring plant roots never became waterlogged. This single innovation transformed barren, vertical slopes into incredibly productive agricultural zones, feeding a vast empire while simultaneously stabilizing the very foundation of their civilization. It was a closed-loop system of stunning efficiency and sustainability, all achieved with little more than arranged stone and an intimate understanding of mountain ecology. Hundreds of years later and a world away, the Romans were tackling a different environmental challenge: water security for their sprawling, thirsty cities. Their answer, the aqueduct, is a monument to sustainable resource management. These weren't just bridges, they were meticulously graded channels that used gravity alone to transport fresh water from distant mountain springs across dozens of miles. By constructing them with precise, mortar-free stonework or durable Roman concrete, they created systems that were not only incredibly efficient, but also self-regulating and low maintenance. The gentle, consistent slope ensured a reliable flow without the need for pumps or external energy. The absence of rigid mortars in many of their earlier aqueducts allowed the stone conduits to flex slightly with ground shifts, preventing cracks and leaks. This sustainable approach to urban planning provided clean water for public baths, fountains, and sewers, drastically improving public health and enabling cities to grow to sizes that wouldn't be seen again in Europe for over 1,000 years. The Romans weren't just moving water, they were orchestrating an entire ecosystem, harnessing natural elevation and hydraulic principles to support urban life on an unprecedented scale. At the heart of this environmental harmony was the dry construction method itself. The absence of mortar, which we might see as a primitive limitation, was actually a sophisticated adaptation. In colder climates where freezing and thawing are constant threats, mortared walls are highly vulnerable. Water seeps into the tiny pores of the mortar and the stone, and when it freezes, it expands with tremendous force, cracking and spalling the surface over time. A dry stone wall, however, is inherently breathable. Water passes freely through the countless small gaps between the stones and drains out the bottom, never trapped long enough to freeze destructively. This same principle applies to seismic activity. As we've seen, a rigid, mortared structure fights against the movement of an earthquake, often leading to catastrophic failure. A dry stone structure is designed to absorb and dissipate that energy, flexing and settling without collapsing. This innate flexibility made ancient structures inherently more resilient to the environmental stresses that routinely destroy modern, rigid constructions. They were designed not for a static ideal of perfection, but for the dynamic, ever-changing reality of the natural world. Even their use of temporary or renewable resources reflects a sustainable mindset that is deeply relevant today. The massive earthen ramps used to build the pyramids, the wooden cranes and scaffolding of the Greeks, the rope and timber levers used to position megaliths, all these were temporary. Once the permanent stone structure was complete, these organic materials could be dismantled, reused, or would simply biodegrade, leaving no permanent scar on the landscape. They built for eternity with stone, but they built their tools of construction from the renewable resources of the forest and the earth. This stands in stark contrast to much of modern construction, which often relies on energy-intensive steel, concrete, and plastics for both temporary and permanent elements, leaving a significant carbon footprint even before the building is occupied. The ancient approach was a model of low-impact, cradle-to-cradle thinking, where the only permanent legacy was the magnificent, purposeful structure itself. Seamlessly integrated into a landscape it was designed to protect and honor for all time. This remarkable resilience in the face of the Earth's raw power stands as one of the most brilliant chapters in the story of ancient engineering. In regions constantly shaped by tectonic forces, builders didn't just construct monuments, they engineered partners in a slow, powerful dance with the planet itself. Their greatest innovation was a fundamental shift in perspective. Instead of attempting to create rigid, unyielding structures to resist seismic energy, a battle that is almost always lost, they designed their buildings to be dynamic participants. They understood that flexibility was the key to survival, and their mortar-free techniques were the perfect vehicle for this philosophy. A wall held together with hard, brittle mortar is like a clenched fist. When struck by the immense, unpredictable force of an earthquake, it has no choice but to shatter. But a dry stone wall with its countless individual blocks is more like an open hand. It can absorb the blow, move with the energy, and then return to its original form. This concept of allowing a building to sway, to shift, and to settle is a principle that modern seismic engineers now call base isolation or energy dissipation, and it is at the very cutting edge of contemporary architectural design. The ancients weren't just building, they were programming a response to disaster directly into the DNA of their stone and wood. The Inca civilization provides the most iconic example of this seismic wisdom. Their architectural masterpiece, the fortress of Sacsayhuaman overlooking Cusco, is a breathtaking case study. The walls, constructed from colossal limestone and diorite blocks, some weighing over 100 tons, are assembled in a zigzag pattern that resembles the teeth of a giant serpent. Each stone is a unique, irregular polygon, with anywhere from 12 to 36 meticulously carved sides and corners. When an earthquake strikes, the energy travels through the ground and into the wall. In a mortared structure, that energy would travel through the rigid adhesive, seeking out the weakest point and exploding it. But in the Inca wall, the energy is immediately broken up and redirected. It travels along the complex network of joints, diffusing and dissipating as it moves from one interlocking stone to the next. The entire wall shudders and shifts, with each block moving minutely against its neighbor. The friction between the stones acts as a natural damper, converting the destructive kinetic energy of the quake into harmless heat and sound. When the shaking stops, gravity and the perfect inward-leaning angle of the walls simply pull each stone back into its original position. This is the famous dance of the Inca stones, a graceful, life-saving performance that has allowed these walls to stand unshaken through centuries of violent tremors. Across the Pacific Ocean, an entirely different culture working with a completely different material arrived at a strikingly similar solution. In Japan, a nation situated on the volatile Pacific Ring of Fire, ancient carpenters developed a seismic-resistant wonder, the multi-story pagoda. Built entirely of wood without a single nail or metal fastener, these slender, towering structures seem incredibly fragile. Yet historical records show that not a single one has ever collapsed due to an earthquake. The secret lies in a brilliant central pillar known as the Shinbashira. This massive, central column of Japanese cypress is not fixed at its base or attached to the rest of the building's frame. Instead, it hangs loosely from the top, almost like a giant pendulum suspended through the heart of the pagoda. Surrounding it is a flexible frame of interlocking beams and brackets that are joined using complex wooden connections that allow for movement and flex. When the ground begins to shake, the entire pagoda sways. The heavy central pillar swings back and forth like a counterweight, its inertia helping to stabilize the structure and absorb the seismic energy. The individual floors are designed to sway out of sync with one another, a phenomenon called phase shifting, which further helps to cancel out the destructive vibrations. It is a system of incredible sophistication, a passive damping mechanism that uses the building's own weight and flexibility to neutralize a threat, all achieved through joinery and an intuitive mastery of physics. The common thread between the stone dancers of Peru and the wooden pendulums of Japan is a profound, observation-based understanding of dynamics. These builders were the original physicists. They learned from centuries of trial and error, watching how different structures responded to tremors. They saw that heavy, rigid things broke, while lighter, flexible things often survived. They noticed that a loose stack of rocks might topple, but an interlocked one might settle. This empirical knowledge, passed down through generations of artisans, became encoded in their building traditions. They weren't working from mathematical formulas, but from a deep, cultural memory of what worked. This approach turned a terrifying environmental challenge into their greatest creative opportunity. The constant threat of earthquakes didn't stifle their architectural ambition. It inspired it. It forced them to innovate, to think more deeply about the relationship between their materials, their designs, and the forces of nature. In doing so, they created a legacy of resilience that has preserved their temples, fortresses, and pagodas as living lessons. Today, as modern engineers grapple with protecting our own cities from seismic threats, they are increasingly looking back to these ancient masters, studying the principles of flexible joints, energy dissipation, and base isolation that were perfected in stone and wood thousands of years ago. To truly grasp the meaning behind these monumental structures, we must look beyond the stones themselves and into the minds and souls of the people who built them. For ancient civilizations, engineering was never a purely practical endeavor. It was a sacred act, a form of physical prayer that connected the earthly realm to the divine. The choice to build without mortar was far more than a technical decision. It was a profound spiritual statement. Mortar, a mixture of crushed materials, was seen by many cultures as impure, temporary, and ultimately weak. A structure bound by such a substance could decay and crumble, but a building made of perfectly fitted stones, where each block met its neighbor in a seamless embrace, was a reflection of cosmic perfection and eternal order. This was architecture as theology, where the precision of a joint was a measure of devotion, and the alignment of a wall with a star was a direct line of communication to the gods. This fusion of the spiritual and the structural is breathtakingly clear in the very forms these buildings took. The Egyptian pyramid was not merely a geometrically stable shape. It was a representation of the Benben, the primordial mound from which all creation sprang, and a physical manifestation of the rays of the sun god Ra, shining down to lift the pharaoh's soul to the heavens. Its perfect, smooth-sided triangle was a symbol of ascension and eternal life, a machine for resurrection built with mathematical certainty. Similarly, the stepped pyramids of the Maya were not just cleverly designed towers. They were symbolic sacred mountains, recreating the mythic landscape of their creation stories and serving as literal bridges between the world of humans and the domain of the gods. The temples atop them were portals, and the staircases were paths for priests and rulers to ascend into a higher state of being during elaborate rituals. The precision required in their construction was therefore absolute, because a misaligned stone or a poorly calculated angle wasn't just an engineering flaw, it was a spiritual failure that could break the connection to the divine and jeopardize the very order of the cosmos. This demand for perfection infused every single step of the construction process with ritual significance. Before a single stone was quarried, priests and astronomers would carefully determine the most auspicious day to begin, aligning the project's inception with specific celestial events. The quarrying of the foundational stone itself was often a ceremonial act, accompanied by offerings and prayers to appease the spirits of the earth being disturbed. In cultures across the world, from the Inca to the ancient Egyptians, the act of moving a massive stone block was a communal ritual. Teams of laborers pulling in unison on great ropes would have been led by chants or rhythmic drums, transforming back-breaking toil into a synchronized performance of faith. The final placement of a cornerstone was a moment of immense importance, often involving the burial of sacred offerings, precious objects, symbolic artifacts, or even ritual sacrifices within the foundations to consecrate the site and seek divine blessing for the entire endeavor. This spiritual imperative was the ultimate driver of innovation. The terrifying responsibility of building a home for a god or a vessel for a king's eternity demanded the absolute best of human capability. It pushed master architects to observe the heavens with unprecedented accuracy, leading to the development of sophisticated astronomy. It compelled mathematicians to calculate load distributions and geometric proportions with flawless precision, giving rise to early engineering principles. The need for perfect, smooth surfaces on granite led to the innovation of using sand as an abrasive. The desire to align a temple doorway with the rising sun on the equinox required the invention of precise surveying tools. In this way, the drive to honor the gods directly fueled the advancement of science and technology. The quest for spiritual perfection became the engine of practical innovation, proving that faith and reason were not opposing forces, but twin pillars supporting humanity's greatest achievements. The enduring legacy of these structures is a powerful testament to this union, reminding us that when we build with a purpose greater than ourselves, we are capable of creating wonders that truly stand the test of time. Despite the incredible progress we have made in understanding these ancient wonders, a profound and tantalizing shroud of mystery still hangs over many of their most basic construction secrets. We can stand in awe of the Great Pyramid or run our hands over the seamless joints of an Inca wall. But when we try to mentally reconstruct the exact step-by-step process from quarry to completion, we inevitably hit a wall of unanswered questions. The most persistent and captivating of these mysteries revolves around the simple, yet monumental, act of movement. How, for instance, did the builders of Stonehenge transport those colossal sarsen stones, some weighing over 40 tons, over 20 miles of rolling English countryside from the Marlborough Downs to Salisbury Plain? The prevailing theory of wooden rollers and sledges makes sense on paper, but experimental archaeologists who have tried to replicate the feat have encountered a cascade of practical nightmares: rollers crushing under the immense weight, sledges bogging down in soft earth, and the sheer, staggering number of people required to coordinate every inch of the journey. The logistics of directing a team of hundreds to pull in unison, to navigate inclines, and to cross rivers with such a precious and cumbersome load is a puzzle of social organization that is just as complex as the engineering itself. This mystery only deepens when we consider the even more ambitious projects. Take the infamous massive stone statues on Easter Island, the Moai. Many of these giants were quarried from the volcanic rock of one crater, Ronoroku, but then transported miles across the island to stand on vast stone platforms called ahu. The most popular theory, supported by experimental archaeology, suggests a rocking, walking motion. Teams of rope pullers would shift the statue from side to side, inching it forward in a process that would have been painstakingly slow but theoretically possible. Yet, this doesn't fully explain how they navigated the island's rugged terrain, or how they ultimately raised the multi-ton statues onto their platforms. Similarly, in Egypt, the transportation of the granite obelisks and the colossal statues of the pharaohs remains a subject of fierce debate. While the image of sledges on watered sand is compelling and supported by tomb paintings, the practicalities of moving an 800-ton stone block, as found in the unfinished obelisk at Aswan, push the limits of what seems physically possible even with thousands of laborers. These are not just academic questions, they are doorways into understanding the true extent of ancient project management, communication, and the sheer force of collective human will. Then there is the equally perplexing challenge of the final placement. How were these behemoths lifted, positioned, and set with such hair-raising accuracy? The construction of the Great Pyramid is the ultimate example. The ramp theory is the most widely accepted explanation for how stones were raised to such great heights, but the exact configuration of these ramps is lost to time. Was it a single, straight ramp growing longer and steeper as the pyramid rose? A spiraling ramp wrapping around the structure's exterior, or perhaps a series of internal ramps within the pyramid's own core? Each theory has its merits and its flaws, and each would have required a completely different set of logistical calculations and a mind-boggling amount of additional material to build the ramp itself, which would have been a massive public works project in its own right. For the massive lintels at the top of Stonehenge, the likely method involved building an earthen mound next to the upright stones, dragging the lintel up the ramp, and then carefully removing the earth from underneath to lower it into place. This sounds simple, but the margin for error was virtually zero. A single mistake in this delicate balancing act could have shattered the prized stone or crushed the workers below. Beyond the how of movement and placement, there is the even more precise mystery of the cuts themselves. How did ancient artisans, working primarily with stone and copper tools, achieve such flawless flatness and such tight joints in incredibly hard materials like granite, basalt, and diorite? We know they used sand as an abrasive with copper saws and drills, but the level of precision seen in the granite coffers inside the Great Pyramid or the mirror-like finishes on some Inca stones suggests a level of skill and patience that is almost incomprehensible. Could they have possessed advanced, yet simple, techniques that have been lost to history? Some researchers point to the possibility of using some form of primitive but effective surface planners or grinding systems that have not survived in the archaeological record. The idea that they might have used plant-based acids to soften the stone surface slightly is another speculative but intriguing theory. The truth is, we may be underestimating the cumulative effect of generations of specialized knowledge. A master stonecutter would have possessed an intuitive, tactile understanding of his material, knowing exactly how to strike it, how to grind it, and how to polish it, turning a lifetime of practice into what looks to us like near magic. These unanswered questions have, inevitably, given rise to more speculative and sensational theories, from the involvement of lost advanced civilizations like Atlantis to extraterrestrial guidance. While these ideas capture the public imagination, they do a great disservice to the ingenuity of our ancestors. The real story is far more compelling. The fact that we are still debating and experimenting with these problems is a testament to the sophistication of ancient engineering. It shows that their solutions were not obvious or simple. They were the result of centuries of experimentation, innovation, and problem-solving. Every time a new theory is proposed or an experiment is conducted, we gain a deeper appreciation for the intelligence and resilience of these ancient cultures. The mysteries are not a sign of their ignorance but of our own. We are still catching up to their understanding of practical physics, material science, and large-scale collaboration. These lingering enigmas ensure that the field of archaeoengineering is alive and thriving, driving us to look closer, to think more creatively, and to never stop being amazed by what human hands and minds can achieve. When we look at the architectural landscape of our modern cities, soaring glass skyscrapers, vast concrete bridges, and sprawling suburban developments, we see a world built on principles of speed, efficiency, and economic scalability. The binding agents of this modern world are synthetic steel rebar, Portland cement, and industrial adhesives. These materials allow us to assemble structures with astonishing rapidity, creating complex forms and achieving heights the ancients could never have imagined. This is engineering optimized for growth and immediate utility, a reflection of a world driven by economic cycles and the pressing needs of a booming global population. The ability to quickly house millions and connect continents with networks of roads and railways is an undeniable triumph of modern innovation. Yet, this approach comes with a hidden trade-off, one that becomes painfully clear when we compare a modern concrete apartment complex, perhaps designed for a 50-year lifespan, with a dry stone Inca wall that has already endured for over 5 centuries. The fundamental difference lies not in capability, but in philosophy and priority. Ancient engineering was an exercise in permanence, a dialogue with eternity where the primary goal was to create something that would last forever, harmonizing with the natural world. Modern engineering, by contrast, is often a negotiation with time and budget, where the goal is to create something that is fit for purpose for a designated period, often with less regard for its ultimate endurance or environmental footprint. This divergence in philosophy is most evident in how the two traditions handle stress and the passage of time. Ancient structures were designed to be dynamic, to breathe and flex with their environment. A dry stone wall, as we've seen, is a masterclass in flexibility. When the ground shifts in an earthquake or the earth settles over centuries, the individual stones can minutely adjust, dissipating energy and settling into a new, stable configuration. They are resilient systems. Modern construction, with its rigid, monolithic use of reinforced concrete, often creates brittle structures. Concrete is incredibly strong under compression but weak under tension, which is why it's paired with steel rebar. However, this steel can corrode over time, especially when exposed to water and salt, causing it to expand and crack the concrete from within in a process known as spalling. This inherent vulnerability means that a modern building requires constant maintenance and has a predictable expiration date, a stark contrast to an ancient temple that grows more stable as its stones settle together over the ages. The ancient method builds in a forgiveness factor, a capacity for self-correction, while the modern method often creates a fixed, static object fighting a losing battle against the elements. The environmental contrast is equally striking. Ancient construction was inherently local and low energy. Builders used materials found on or near the site, stone from a nearby quarry, timber from a local forest, earth from the ground beneath their feet. The energy input was almost entirely human and animal labor. This resulted in an extraordinarily low carbon footprint. A Roman aqueduct, for all its grandeur, required little more than stone, lime, and human effort. Compare this to the production of modern Portland cement, a key ingredient in concrete, which is responsible for approximately 8% of global carbon dioxide emissions due to the intense heat required in its kilns. The modern construction ecosystem is also globalized, with materials often traveling thousands of miles. Steel from one continent, specialty glass from another, rare hardwoods from a third, all consuming vast amounts of fossil fuel energy in transport. The ancient way was a closed-loop system. The modern way is a global, energy-intensive network with a heavy environmental cost. Yet, it would be a mistake to view this comparison as a simple condemnation of modern methods. The scale and complexity of what we build today is, in its own right, breathtaking. Modern engineering allows us to suspend roadways over vast canyons, build tunnels under oceans, and create climate-controlled environments in the desert. We can construct hospitals, data centers, and research facilities that require a level of environmental control and technical integration unimaginable in the ancient world. The ability to do this quickly and for a growing population is a monumental achievement. The point is not that one approach is universally better, but that each serves a different master. Ancient engineering served the gods' eternity and the slow, patient rhythm of the natural world. Modern engineering serves the economy, immediate human need, and the rapid pace of societal change. The most exciting development in contemporary architecture is the growing movement to bridge this philosophical divide. Modern engineers and architects are now actively looking to the past for wisdom, creating a new field often called bio-inspired or vernacular design. They are relearning the ancient lessons of passive sustainability. Instead of fighting the sun with energy-guzzling air conditioning, new buildings are designed with strategic overhangs and natural ventilation channels, much like the thick, insulating walls of a Mediterranean stone hut. The principle of seismic flexibility, so brilliantly mastered by the Incas and the Japanese, is being reinvented in the form of base isolators, giant rubber, and lead pads placed under modern buildings that allow them to sway safely during an earthquake, a direct homage to the dancing stones of Sacsayhuaman. There is also a renewed appreciation for massive, durable materials that regulate temperature naturally. The use of rammed earth, a technique thousands of years old, is seeing a resurgence in high-end sustainable homes for its beautiful aesthetics and incredible thermal mass, which keeps interiors cool in summer and warm in winter without any mechanical help. This reevaluation forces us to ask a profound question: what truly constitutes advanced engineering? Is it the complexity of our materials and the speed of our assembly? Or is it the elegance of a solution that requires minimal energy, creates zero waste, and endures for millennia? The ancient builders demonstrate that advanced engineering can be the quiet, profound understanding of a material's innate properties and the clever application of fundamental physics. Their mastery was not in overcoming nature with superior technology, but in partnering with it through superior insight. They prove that sometimes the most sophisticated solution is not to add more complexity, but to strip it away, to rely on geometry, gravity, and friction, the universal constants that will never fail. As we face the pressing global challenges of climate change and resource scarcity, this ancient definition of advancement becomes not just interesting, but essential. The future of resilient construction may not lie in inventing a new, high-tech adhesive, but in rediscovering the timeless, powerful elegance of a perfectly cut stone, locked into place by the unwavering force of gravity, and designed to stand as a testament to human ingenuity long after our steel has rusted and our concrete has turned to dust. Long before the pharaohs dreamed of pyramids and 1,000 years before the engineers of Stonehenge arranged their first stone, a remarkable society on the small Mediterranean islands of Mortar was embarking on an architectural revolution that still defies belief. The megalithic temples of Mortar are not just old, they are foundational, representing the very dawn of monumental architecture in the Western world. Constructed beginning around 3600 BCE, these complexes are the oldest freestanding stone structures on Earth, a title that alone should command our awe. Imagine the context. Europe was still deep in the Neolithic period, with most communities living in wooden or simple stone huts. Yet on these islands, a culture with no metal tools, no written language, and no knowledge of the wheel was somehow quarrying, transporting, and erecting limestone blocks weighing many tons, fitting them together with a vision that was both structurally sound and spiritually profound. The scale of their ambition is immediately apparent at sites like Haga Kim or Mnajdra, where the great stone walls curve inward to form a series of semicircular chambers, creating a layout that resembles a cloverleaf. The builders worked with the local Globigerina limestone, a relatively soft stone that was easier to shape with their primitive stone tools but also more vulnerable to the elements. Their construction method was a masterclass in dry stone technique. Each massive block was carefully selected and roughly shaped at the quarry, likely using stone mauls and wooden wedges. The real genius, however, was in the movement and placement. Archaeologists have found large, spherical stone balls scattered around the temple sites, and the prevailing theory is that these acted as primitive rollers. Teams of workers would have levered a massive block onto a track of these stone balls, using wooden levers to slowly, painstakingly roll it forward, retrieving the rollers from the back to place them at the front in a continuous, grueling process. To lift these multi-ton blocks into position, they almost certainly built massive earthen ramps and used timber frameworks as crude cranes, employing ropes made from animal hides or plant fibers to haul the stones upward inch by inch. Once in place, the precision of their work becomes clear. The walls were built using a combination of enormous orthostats, large, upright stones filled in with smaller, meticulously stacked masonry. But the Maltese builders didn't stop at simple walls. They pushed the boundaries of design with one of the world's earliest uses of corbelling. This technique involves stacking successive courses of stone slightly inward from the one below, gradually narrowing the gap until it can be capped by a single slab. This allowed them to create domed roofs and arched doorways, inventing a way to span space and create enclosed or inspiring interiors without any knowledge of the true arch. The temples also feature intricate features that reveal a sophisticated understanding of their craft, such as carefully drilled holes that likely held ropes or fittings for doors, and stone altars with elegantly carved spirals. The most stunning example of their architectural daring is at the Hal Saflieni Hypogeum, an enormous, multi-level subterranean temple complex carved directly into the living rock, mirroring the designs of the above-ground temples in a breathtaking feat of reverse engineering. This was not random construction. Every aspect was deeply intentional, blending the practical with the celestial. The temples are precisely aligned to the movements of the sun and stars, functioning as massive stone calendars. The most famous alignment is at the Mnajdra temple, where during the spring and autumn equinoxes, the first rays of the sun pierce the main doorway and illuminate a specific stone slab deep within the central corridor. During the summer and winter solstices, the sunlight cuts along the edges of large stone blocks, creating sharp lines of light and shadow that mark the changing of the seasons with unquestionable accuracy. This celestial connection tells us that these structures were far more than mere gathering places. They were the beating heart of a complex cosmological belief system. The architecture itself was a physical manifestation of their understanding of the universe's cycles, a permanent, stone-bound link between the earthly realm and the celestial order. The spiritual life that pulsed within these walls is hinted at through the art left behind. The temples are adorned with carvings of spirals, trees, and animals, but most notably with countless figurines of voluptuous, often headless female figures. These so-called fat ladies or mother goddess statues suggest a society that venerated fertility and the life-giving forces of nature. The discovery of altars with carved bowls that still show evidence of animal sacrifice, along with the remains of thousands of people found in the hypogeum, points to a culture deeply engaged in rituals concerning life, death, and rebirth. The sheer amount of labor invested, scholars estimate that the largest temples would have required thousands of person-days to complete, indicates a highly organized society capable of mobilizing and sustaining a large workforce, likely directed by a powerful priestly class. The temples were the central project that united the community, giving them a shared purpose and a common identity tied to the land and the sky. Then, around 2500 BCE, this vibrant temple-building culture vanished almost as mysteriously as it appeared, leaving behind their silent stone sentinels. Their legacy is a powerful testament to what human communities can achieve through shared belief, patient innovation, and a deep desire to build something permanent that speaks to the cosmos. While the grand pyramids and temples capture our imagination with their scale and spiritual weight, the true genius of dry stone construction is perhaps even more beautifully expressed in its humbler, more intimate forms. Nestled in the sun-drenched region of Puglia in southern Italy, the town of Alberobolo presents a scene that feels almost like a fairy tale. Here, covering the slopes of two small hills, is a breathtaking collection of over 1,500 whitewashed conical stone structures known as trulli. These unique dwellings, with their dark, mysterious pinnacles and symbols painted on their roofs, are not ancient relics frozen in time. They are a vibrant, living neighborhood, a UNESCO World Heritage Site where people still live, work, and maintain a building tradition that is a masterclass in practical, clever, and adaptable engineering. The construction of a trullo is a fascinating process that turns the principles of dry stone masonry into a three-dimensional puzzle. Unlike the massive, irregular blocks of the Incas, the trulli are built using thousands of thin, flat slabs of local limestone known as chainquel. The builder, or trullero, begins by laying a perfectly level circular foundation of larger stones. Then, working entirely without scaffolding or wooden frameworks, they start the meticulous process of building the walls inward. Each successive course of limestone slabs is laid slightly closer to the center than the one below, creating a corbelled effect that gradually curves upward and inward. The skill lies in selecting each stone for its specific size and shape, ensuring that its weight and angle contribute to the overall stability of the growing dome. The final stones at the very top, the final piece of the stone puzzle, lock the entire structure into a state of perfect compression, where every element is held in a delicate balance by the force of gravity and the precise friction between the stones. The iconic conical or domed roof is then capped with a decorative pinnacle, often a sphere, disc, or cross, which serves the crucial function of sealing the structure from the weather and weighing down the apex to ensure its stability. This ingenious building method was born from a combination of environmental necessity and political cunning. The region of Puglia is rich with the raw material limestone that naturally fractures into these perfect, workable slabs, but poor in timber for beams and scaffolding. The dry stone technique was a brilliant adaptation to the local resources, but the story takes a more intriguing turn with a clever historical twist. During the 16th and 17th centuries, the area was under the control of the powerful Acquaviva family, the Counts of Conversano. The Kingdom of Naples, which ruled over the region, imposed a hefty tax on any new permanent settlement. The Counts, eager to expand their agricultural lands and populate them with peasant farmers without incurring this tax, allegedly devised a clever loophole. They instructed their tenants to build their homes without any mortar whatsoever. This meant that, by the strict legal definition of the time, the structures were not considered permanent dwellings but rather temporary shelters. The legend goes that if a royal tax inspector was spotted traveling to the area, a signal would be given, and the farmers would quickly dismantle the key stones of their roofs, causing the entire structure to partially collapse into a mere pile of stones, thus avoiding the tax. Once the inspector left, the stones could be reassembled with relative ease. While historians debate the absolute truth of this tale, it powerfully illustrates the incredible adaptability of this construction style. A trullo was not just a home, it was a tool of economic resistance, a structure designed for both assembly and disassembly with astonishing speed. Beyond their political cleverness, the trulli are marvels of passive climate control and environmental design, showcasing an intuitive understanding of bioclimate architecture long before the term was invented. The thick, double-skinned walls of limestone act as a natural thermal mass. During the scorching Mediterranean summers, the dense stone absorbs the heat from the outside air, keeping the interior spaces remarkably cool and comfortable. At night, as the temperatures drop, the stones slowly release the stored heat, moderating the internal climate. In the winter, this process reverses. The walls absorb any heat generated inside from a fireplace or cooking, radiating it back slowly to ward off the chill. The small windows, a necessity of the construction method, further help to minimize heat gain in the summer and heat loss in the winter. This natural insulation system creates a stable, energy-efficient living environment that requires no mechanical heating or cooling, a timeless lesson in sustainable design that modern architects are only now fully appreciating. Walking through the narrow, winding streets of the Rione Monte district in Alberobello today is an immersive experience in this living architectural tradition. The whitewashed walls gleam under the Italian sun, and the gray stone roofs, often decorated with mysterious white painted symbols, primitive zodiac signs, Christian icons, or magical charms, add a layer of cultural depth and personal expression to the structures. Many of these trolli have been continuously inhabited for centuries, their walls and domes maintained and repaired using the same techniques and materials, a testament to the durability and timeless appeal of the design. Some have been converted into charming shops, cafes, and boutique hotels, allowing visitors to step inside and experience the unique atmosphere of these stone spaces, the cool quiet, the soft light filtering in from a small window, and the awe-inspiring sight of the interior dome, where each stone is visible in a complex spiral reaching up to the apex. The trulli of Alberobello stand as a powerful counterpoint to the narrative of ancient engineering being solely about monumental grandeur. They prove that the same principles of compression, friction, and intelligent material use could be applied to create not just temples for the gods, but comfortable, beautiful, and resilient homes for everyday people. They are a living dialogue between human needs and natural materials, a story of adaptation, cleverness, and the enduring power of simple, brilliant design. This ancient conversation with stone and gravity is not a forgotten language. It is experiencing a powerful and inspiring revival in the world of modern architecture, as contemporary designers and engineers look to the past to solve some of the most pressing challenges of our future. In an era defined by climate change and a growing awareness of our environmental footprint, the principles of dry stone construction offer a blueprint for sustainability that is both timeless and urgently relevant. Today's architects are not simply copying old forms. They are reinterpreting this ancient wisdom, integrating age-old techniques with cutting-edge technology to create buildings that are beautiful, resilient, and deeply respectful of the planet. We see this not in grand pyramids, but in thoughtful projects like modern dry stone retaining walls that prevent erosion along highways, or in stunning eco-homes that use locally sourced, uncut stone to create walls that breathe and regulate temperature naturally. These structures carry a minimal carbon footprint as they forego the energy-intensive production of concrete and steel, instead relying on the inherent strength and beauty of materials provided by the local landscape. This is a movement away from the one-size-fits-all globalized construction model and toward a more thoughtful, region-specific architecture that celebrates its place in the world. The lessons from history are also fundamentally reshaping how we design for safety in an unstable world. Modern seismic engineers now meticulously study the dynamic behavior of Inca walls and Japanese pagodas, using sophisticated computer models to understand exactly how these structures dissipate energy. This research has directly influenced the development of base isolation systems, where modern buildings are placed on massive rubber and lead bearings that allow them to sway safely during an earthquake, much like the dancing stones of Sacsayhuaman. The ancient understanding of flexibility over rigidity is now a cornerstone of seismic codes in earthquake-prone regions. Similarly, the Roman mastery of arch and vault construction, which used compression to span great distances, informs the design of modern bridges and tunnels, proving that the most elegant structural solutions are often those that work with physics rather than against it. This fusion of old and new is a testament to the fact that advanced engineering is not always about inventing something new, but about rediscovering and validating the profound intuitive knowledge of our ancestors with the tools of modern science. This philosophical shift is powerfully embodied in the growing vernacular architecture movement, which champions building practices that are intrinsically tied to a specific place and culture. It is a conscious rejection of the bland, identical glass and steel towers that have come to define so many modern cities. Instead, practitioners of vernacular architecture look to local traditions, using locally sourced materials and indigenous craftsmanship to create structures that are uniquely suited to their climate and cultural context. A beautiful example can be found in the modern rammed earth buildings now appearing in Australia and the American Southwest. This technique, ancient in its origins, involves compacting layers of local soil, clay, and a small stabilizer into forms to create massively thick, solid walls. The result is a building with incredible thermal mass that stays cool in blistering heat and warm in chilly desert nights, all while having an aesthetic texture and color that literally emerges from the earth it stands on. This approach supports local economies, reduces transportation costs, and creates a deep, palpable connection between a structure and its environment, something that has been largely lost in contemporary construction. Perhaps the most enduring legacy of these ancient engineers is the powerful reminder that true innovation does not require overwhelming complexity. In a world chasing the next high-tech material or digital fabrication method, the enduring presence of a 4,000-year-old pyramid is a humbling and inspiring counterpoint. It shows us that the most sophisticated solutions can be breathtakingly simple, rooted in a deep observation of nature and a mastery of fundamental principles. The perfect balance of a stone lintel, the clever interlock of a puzzle-like wall, the gentle curve of an arch, these are not primitive ideas. They are the distilled essence of structural logic refined over millennia. By looking to the past, we are not turning our backs on progress. We are building a more thoughtful future, one that honors the wisdom of heritage while embracing the possibilities of new technology. It is a future where buildings are not just places to live and work, but active partners in environmental stewardship, designed for harmony with nature and built to stand as a testament to human ingenuity for generations yet to come. Preserving these ancient wonders built to last for millennia presents a paradox of modern conservation. How do we protect structures designed to be maintenance-free without inadvertently causing their demise? The very absence of mortar that granted them such resilience now demands an incredibly delicate touch. Modern conservation philosophy, guided by charters like Venice's, insists that any intervention must be minimal, reversible, and above all, respectful of the original material and method. This means that a crack in an Inca wall cannot simply be filled with modern epoxy or cement. Such materials are far stronger and less permeable than the surrounding ancient stone. They trap moisture inside, create hard, rigid points that can cause further cracking during seismic activity, and introduce salts that can slowly crystallize and explode the stone from within. The solution must be as elegant as the original construction, finding a stone with a near-identical geological composition and carefully shaping it to fit the gap, sometimes using nothing more than a traditional lime-based slurry that is softer and more compatible than modern alternatives. This is conservation as a form of archaeological surgery, where every action is taken with the utmost precision and a deep understanding of the patient's unique physiology. The execution of this philosophy falls to a vanishing breed of artisans, the true inheritors of these ancient crafts. Restoring a dry stone wall isn't a job for a general contractor. It requires a master stonemason who can read the language of the stones, understanding the specific logic behind why each irregular block was placed in a particular position and orientation. These specialists train for decades, learning to shape granite with a hammer and chisel by feel and sound, replicating the ancient tool marks so that new work is indistinguishable from the old. The problem is that these skills are disappearing. In a globalized economy, there are far more lucrative and less physically demanding career paths than spending a year painstakingly resetting the stones of a remote archaeological site. Projects now often face the difficult task of locating these rare experts and recruiting apprentices willing to dedicate their lives to this slow, meticulous work. Organizations like UNESCO are trying to combat this by establishing living heritage programs and international workshops, aiming to codify this tacit knowledge and pass it on to a new generation before the last masters are gone. Without them, we risk being left with monuments we can admire but no longer truly understand how to fix. Beyond the immediate physical repair, these sites face an onslaught from environmental threats that their original builders never could have anticipated. The same air that gives life now carries invisible agents of decay. Industrial pollution and acid rain slowly eat away at limestone surfaces, dissolving intricate carvings and smoothing away sharp edges that have survived for thousands of years. In coastal regions, salt spray from the sea penetrates porous stone, only to crystallize inside during dry periods, exerting immense pressure that can spoil and flake the surface away like old paint. Perhaps the most insidious threat is climate change. More frequent and severe weather events, torrential rains, prolonged droughts, and extreme freeze-thaw cycles subject ancient masonry to stresses it was never designed to withstand. In Peru, archaeologists are now monitoring Inca sites with drones and satellite imagery to track how shifting precipitation patterns are affecting groundwater levels and slope stability, potentially undermining the very foundations of these timeless structures. This new reality demands a proactive, scientific approach to conservation, moving from simply fixing damage to predicting and preventing it through constant environmental monitoring. Then there is the double-edged sword of their own fame, tourism. These sites were built for gods and kings, not for millions of visitors each year wearing down the stone with their footsteps. The constant vibration from foot traffic on a stone staircase can gradually loosen joints that have been stable for centuries. The oils from human hands, gently touching a wall for a photograph, accumulate over time and degrade the stone's surface. Managing this impact is a constant battle. Solutions range from the simple building, sophisticated viewing platforms, and designated pathways that keep crowds at a safe distance, to the technologically advanced, like the timed ticketing systems and visitor caps now employed at Machu Picchu to prevent overcrowding. Some sites have even experimented with virtual reality experiences that allow visitors to explore sensitive areas without setting foot near them. The goal is not to keep people away, but to create a sustainable model where education and access can coexist with the primary duty of preservation. After all, these structures only hold meaning if they can inspire awe in the people who come to see them, but that awe must be channeled into respect and protection. Confronting this web of challenges requires a global commitment. It is a mission that stretches far beyond the capacity of any single nation or organization. The cost of proper conservation is astronomical, often running into the millions for a single site. This necessitates robust international funding from bodies like the World Monuments Fund, coupled with partnerships between governments, academic institutions, and private philanthropists who recognize that this heritage belongs to all of humanity. Equally important is the role of local communities. When people living near these sites are engaged as stewards, receiving education and economic benefits from their preservation, they become their most powerful guardians. Ultimately, safeguarding these monuments is about more than just maintaining piles of rock. It is about preserving a library of human ingenuity, a testament to what we are capable of when we work in harmony with the world around us. The choices we make today will determine whether these silent teachers are still here to inspire the thinkers, engineers, and dreamers of tomorrow. Perhaps the most profound lesson whispered to us from these ancient stones is the art of turning limitation into liberation. We live in an era of seemingly infinite choice, with global supply chains delivering any material imaginable to a construction site. Yet, this abundance can paradoxically stifle creativity. The ancient engineer, faced with only the local limestone, the nearby river clay, and the timber from the forest, had no choice but to become an intimate expert. They had to understand the granular personality of that limestone, how it fractured, how it weathered, how it bore weight. This deep, localized knowledge forced innovation. The Inca, surrounded by earthquake-prone mountains and possessing only bronze tools softer than their granite, didn't try to invent a harder metal. They invented a structural system that danced with the tremors. Their constraint became the mother of their most brilliant invention, seismic resilience through flexibility. This teaches us that true creativity isn't always born from more options, but from a deeper engagement with the options we already have. It encourages a mindset of deep simplicity, where the goal is not to add complexity to overcome a challenge, but to understand the challenge so fundamentally that the solution becomes elegantly straightforward. This philosophy extends directly into our most pressing modern imperative, sustainability. The ancient world operated on a closed-loop system that modern engineers are now desperately trying to replicate. When a Roman aqueduct was built, the primary energy input was calories from food consumed by the laborers and animals. The materials were stone, earth, and lime, all sourced from the immediate region, and the design was meant to function for centuries with minimal maintenance. Compare this to the life cycle of a modern building, which involves energy-intensive manufacturing of steel and concrete, global transportation of components, and a predicted lifespan that often feels shockingly short. The ancient approach offers a masterclass in life cycle analysis. They built for permanence, calculating the long-term value of a structure over generations, not just its short-term economic cost. This long-term perspective is exactly what we need to combat the throwaway culture contributing to climate change. By studying how they used local materials, we learn to reduce embodied carbon from transportation. By understanding their passive climate control, like the thermal mass of a Trullo's walls or the natural ventilation of a Greek temple, we can design buildings that require far less energy to heat and cool. Their methods provide a proven blueprint for constructing a world that doesn't fight the environment, but works in concert with it. For the next generation of architects, engineers, and designers, these ancient sites are not ruins. They are the world's most enduring textbooks. A student of physics can walk through the hypostyle hall in Egypt and see the principle of load distribution made manifest in its towering columns. A materials scientist can analyze the crystalline structure of Inca granite to understand why it has resisted weathering for 500 years. A civil engineer can study the cross-section of a Roman road to understand layered compaction and drainage. This is interdisciplinary learning at its most powerful, where abstract principles from science and math classes suddenly snap into concrete, tangible reality. History is no longer a list of dates but a story of human problem solving. Engineering is not just equations but the art of creating lasting beauty. This fusion of disciplines is crucial for tackling the multifaceted problems of the 21st century, which refuse to stay neatly categorized. We need thinkers who can blend historical wisdom with cutting-edge technology, who can see the connection between a 2,000-year-old aqueduct and a modern water conservation system. Ultimately, the greatest gift from these master builders is a shift in perspective. They compel us to redefine what we consider advanced. Is a building advanced because it is made with a complex composite material fabricated in a distant country and assembled with robotic arms? Or is it advanced because it is crafted from local stone, designed to withstand earthquakes for millennia, regulate its own temperature without machinery, and at the end of its life, return seamlessly to the landscape without leaving a toxic trace? The ancient world argues powerfully for the latter. Their legacy is a call to prioritize resilience over convenience, longevity over speed, and harmony over domination. It empowers us to look at the resources immediately around us with new eyes, to value the knowledge of local craftspeople, and to design with a profound sense of responsibility for the future. By honoring their past, we are not copying their stones, but embracing their spirit of intelligent adaptation, proving that the most sustainable path forward might just be found by looking back. It's tempting to look at these impossible-seeming structures and reach for otherworldly explanations. The idea that aliens guided human hands or that a lost, hyper-advanced civilization provided the technology is a popular and seductive narrative. It turns our ancestors into passive recipients of knowledge rather than the active, brilliant innovators they truly were. This myth, however appealing, does a profound disservice to the immense capabilities of ancient people. It dismisses their ingenuity as something humans simply couldn't achieve on their own, ignoring the mountains of archaeological evidence that tell a much more compelling story. The real mystery isn't how extraterrestrials might have helped, it's how human beings with nothing but patience, observation, and collaborative effort accomplished these feats. The truth is far more inspiring than any fiction. Consider the claim of impossible precision, often cited by those who doubt human capability. How could the Inca, without modern tools, make stones fit together so perfectly that not even a razor blade can slip between them? The answer isn't magic, it's a masterful application of simple, repetitive techniques. Experimental archaeologists have demonstrated this time and again. Using nothing but stone hammers, sand abrasives, and a process of trial and error, skilled artisans can, over a long period, shape hard granite with astonishing accuracy. They would have used a technique called lick and stick, repeatedly rubbing a new stone against an already placed one with an abrasive slurry in between. The high spots on the new block would be slowly worn down until the two surfaces mirrored each other. This isn't a quick process, it requires immense patience and a deep, tactile understanding of the material. But it is entirely possible, and the results speak for themselves. What seems like an impossible task to us, with our modern mindset geared toward speed and efficiency, was simply a matter of dedicated, generational effort for them. Time was a resource they had in abundance. Furthermore, these myths are often tinged with a subtle, lingering cultural bias. There's a tendency to view non-Western achievements through a lens of skepticism that isn't always applied to European monuments. The grandeur of the Roman Colosseum or the Greek Parthenon is celebrated as a triumph of human genius, while the same scale of accomplishment in the Andes or Mesoamerica is sometimes met with disbelief and attributed to outside forces or even Atlantis. This perspective fails to recognize that intelligence and ingenuity are universal human traits. Sophisticated engineering and astronomical knowledge emerged independently all over the globe, from the astronomically aligned temples of Mortar to the earthquake-resistant pagodas of Japan. The Inca developed their seamless masonry for specific seismic reasons. The Maya engineered their corbel vaults to create soaring temples in a jungle environment. Each culture solved the architectural problems presented by their unique environment and beliefs, and their solutions were brilliantly adapted to their specific context. To suggest they needed outside help is to ignore the diverse and powerful evidence of their own independent intellectual journeys. By embracing the factual, evidence-based narrative, we don't lose a sense of wonder, we enhance it. The idea that aliens built the pyramids is a simplistic, off-the-shelf answer that requires no further thought. But understanding that thousands of skilled workers leveled the Giza plateau using water-filled trenches, aligned the sides to true north by tracking stars, and moved multi-ton blocks with sledges and wet sand, that is a story that truly inspires awe. It's a story of incredible human coordination, of problem-solving on a monumental scale, and of a shared cultural will to create something eternal. This grounded perspective connects us more deeply to our ancestors. We can look at a perfectly fitted joint in an Inca wall and see not a mystery, but the fingerprint of a highly skilled stone mason. We can see the years of their life, their pride in their craft, and their contribution to a community project that would outlive them by centuries. That human connection is far more powerful and meaningful than any speculative fantasy. It fosters a genuine admiration for what people can achieve through collaboration, perseverance, and a profound understanding of their natural world. The silent stones of the past are finally beginning to speak, not through whispers, but through a flood of precise digital data. We are living in a new golden age of archaeological discovery, not because we're finding more ruins, but because we are learning to see the ones we have in an entirely new light. The most powerful tools in this modern exploration are not bigger shovels, but non-invasive technologies that allow us to peer through time and stone without ever touching a surface. High-resolution 3D laser scanning is now commonplace, creating billion-point digital twins of entire sites like Machu Picchu or the Great Pyramid. These aren't just simple photographs, they are hyper-accurate point clouds that can be analyzed, measured, and rotated on a computer screen, allowing researchers to detect patterns of tool marks, measure wear from erosion, and even virtually reconstruct collapsed sections with millimeter accuracy. This technology captured the exact sway of Japan's ancient pagodas during recent earthquakes, providing hard data on the dynamic movement that has kept them standing for centuries. Beyond the surface, other tools are mapping the unseen. Ground-penetrating radar sends pulses of energy into the earth, painting a picture of buried foundations, hidden chambers, and long-filled quarry trenches, revealing the complete footprint of a site without a single excavation. At the ancient Maya city of Decode, this technology has revealed a vast, hidden network of houses and reservoirs, completely rewriting our understanding of its population size and urban planning. Similarly, LiDAR, which uses lasers from aircraft to strip away the jungle canopy, has unveiled entire lost cities in Cambodia and Central America, proving that our maps of the ancient world are still filled with vast blank spaces. Material science has also become a key detective. Using portable X-ray fluorescence analyzers, scientists can now determine the exact chemical composition of a stone block while standing at the top of a pyramid, tracing it back to its specific quarry source. This allows them to reconstruct ancient logistics networks, understanding the trade routes and political power required to move materials from one end of an empire to the other. We are no longer just guessing about the past, we are forensically auditing it. This revolution is fueled by a powerful new spirit of collaboration, breaking down the old walls between academic disciplines. The romantic image of the lone archaeologist with a brush and notebook has been replaced by integrated teams where a materials scientist might explain the crystalline structure of granite to a computer modeler, who then works with a stonemason to test a new theory about how Egyptian drill bits were used. Traditional knowledge, once at risk of being lost forever, is now recognized as a critical piece of the puzzle. In Peru, archaeologists are actively working with the descendants of the Inca, the Quechua people, whose oral histories and cultural understanding of the landscape provide context that no radar can detect. They might explain the spiritual significance of a particular rock formation that served as a quarry, adding a layer of meaning to the geological data. This fusion of cutting-edge technology and enduring indigenous wisdom is creating a more holistic and respectful form of exploration, where the goal isn't just to extract information but to collaboratively preserve a shared human heritage. The questions driving this research are as practical as they are profound. How exactly was a 1,000-ton obelisk raised from a horizontal to a vertical position using only manpower and rope? How were the acoustic properties of certain ancient chambers, like the one in Chichen Itza where a clap echoes as the chirp of the sacred Quetzal bird, intentionally engineered? The answers emerging are already reshaping our understanding. Researchers using these new tools have found evidence of much more extensive and sophisticated use of temporary infrastructure than previously believed. The debate over the Egyptian pyramid ramps, for instance, is being informed by digital terrain analysis that models the most efficient and stable slopes, suggesting a combination of straight and zig-zagging ramps built directly into the pyramid's core. The mysteries are not being solved with a single eureka moment, but through the slow, meticulous accumulation of data points that are gradually filling in the gaps in our knowledge. Perhaps the most exciting aspect of this journey is its unexpected feedback loop into our own future. The field of robotics is looking intently at the past for inspiration. How did ancient builders transport 50-ton stones over 20 miles of rugged terrain? The answer likely involves a sophisticated understanding of balance, friction, and coordinated movement principles that are directly applicable to the development of advanced robotics for logistics and construction. Boston Dynamics and other firms study human and animal biomechanics for their robots. Now, they can also study the collective biomechanics of a 200-person team moving a megalith. Similarly, the passive cooling systems of the trolley in Italy or the natural seismic damping of Inca walls are providing real-world, time-tested case studies for modern sustainable architects and engineers. These ancient structures are essentially long-term performance reports on material behavior, offering invaluable data that we could never replicate in a short-term lab experiment. They show us what truly works over the scale of centuries. This ongoing exploration promises a future where the divide between the ancient and the modern becomes increasingly blurred. We are moving toward a world where we won't just look at these sites, but will be able to step into fully immersive virtual reality simulations of their construction, witnessing thousands of digital workers recreate the raising of a stone using the most up-to-date theories. Artificial intelligence is being trained on vast databases of tool marks and architectural styles to help identify the work of specific artisan groups or propose new construction sequences we haven't yet considered. Each technological advance, from more sensitive radar to more powerful computational models, gives us a new lens through which to view our history. The journey to understand these ancient engineers is far from over. In many ways, it has just begun with a new set of eyes. Every scan, every radar pulse, and every collaboration brings us closer to hearing the full story these master builders have been waiting millennia to tell. From the Inca's seamless stone walls that dance with earthquakes to Egypt's celestial pyramids aligned with the stars, these ancient master builders have left us a legacy that is far more than just stone and mortar. It is a testament to what humanity can achieve with nothing but ingenuity, patience, and a profound respect for the materials provided by the earth. Their methods, intentionally free of nails and modern adhesives, were not a limitation but a brilliant choice, one that has granted their creations an immortality that much of our own modern construction can only envy. They understood that true strength doesn't come from forcing materials together with synthetic binders, but from working in harmony with the fundamental principles of physics, geometry, and the natural world itself. This philosophy of construction speaks to a deeper wisdom about resilience, sustainability, and the incredible power of human collaboration. As we stand here today, facing our own monumental challenges of climate change, resource scarcity, and the urgent need for sustainable design, these ancient wonders offer more than just historical curiosity. They provide a powerful source of inspiration. They are a living library of proven solutions, a catalogue of ideas that have been tested not in a lab for a few years, but in the real world for millennia. The passive cooling of an Italian trullo, the seismic flexibility of an Inca wall, the water management of a Roman aqueduct, these are not primitive concepts. They are sophisticated, bio-inspired design principles that are more relevant now than ever before. They challenge us to rethink our definition of advanced engineering, suggesting that the most sophisticated solution is often the one that is simplest, most durable, and most in tune with its environment. The ancient world teaches us that we can build a future that doesn't fight against nature, but collaborates with it, creating structures that are not only resilient but also regenerative. So the next time you see an image of the Great Pyramid or find yourself marveling at the precision of a stone wall, let that sense of wonder sink in a little deeper. Think about the generations of knowledge, the coordinated effort of thousands of hands, and the sheer will to create something beautiful and lasting. Consider how their mastery of patience and deep observation might apply to the problems we are trying to solve today. We would love to hear which of these ancient wonders resonates most with you and what lessons you think we should carry forward into the future. Share your thoughts in the comments below, and if you enjoyed this journey through the mysteries of our past, be sure to subscribe and hit the bell so you don't miss our next exploration into the incredible ingenuity of